Okay, we continue our discussion on matrices of a graph. So far we discussed incident matrix and cycle matrix and the related one fundamental cycle matrix of a graph. So in this video we are going to discuss another kind of matrix related to a graph called cut set matrix and a reduced version of cut set matrix, what is called a fundamental cut set matrix of a graph. So let me start by giving the definition of a cut set matrix. Okay, so a cut set matrix is defined as follows. Let G be a graph with m edges and q cut sets. So cut set is a set of edges whose removal disconnects the graph, whereas the proper subset of those edges, it won't disconnect the graph. Okay, I think that is the definition, and if you want to see the definition, you can look at the video related to that definition. Okay, so let G be a graph with m edges and q cut sets. For example, if you look at this particular graph, here these dotted lines corresponds to different cut sets. So this corresponds to one cut set. So we can see that if you delete this cut set C2, okay, so here the edges are labeled by E1, E2, etc., and the cut sets are labeled by C1, C2, C3, C4, etc. So here we can see that if you delete these two edges, the graph will become disconnected. Similarly, if you delete this cut set C1, which contains this edge E8, the graph will become disconnected, and so forth. For example, C6, it contains these two edges E4 and E6, and if you delete those two edges from this graph, the graph will become disconnected. Okay, so that's what a cut set is, and we can very easily see that deletion of a proper subset of those cut sets, it won't delete the graph. Okay, anyway, that is related to definition of a cut set. Okay, so here we are discussing about cut set matrix. So let G be a graph with m vertices and q cut sets. So here if you look at this particular graph, we can see that it has 8 edges E1, E2 up to E8, and 8 cut sets C1, C2, C3, C4, C5, C6, C7 and C8. So the cut set matrix denoted by C, okay, it is going to be a Q by M matrix, where Q is the number of cut sets and M is the number of edges of G. Okay, it is going to be a 0, 1 matrix. It is going to be a 0, 1 matrix with, and the entries of the matrix are defined as follows. And the entries of the matrix are defined as follows, with Cij equal to 1 if the ith cut set contains the jth edge, and equal to 0 otherwise. Okay, so let's go through an example and see how to define a cut set matrix. So let's consider this graph G. Okay, so this is our graph G, and this graph G has 8 edges and 8 cut sets. The cut sets are labeled C1, C2 up to C8, and the edges are labeled E1, E2 up to E8. And okay, so this is going to be the cut set matrix of this graph G. Okay, so this is going to be the cut set matrix of this graph G. So since it has okay, 8 cut sets, so here this Q is going to be equal to 8, where Q is the number of cut sets in this graph, and M, the number of edges in this case, it happens to be 8. So our cut set matrix, it is going to be a 8 by 8 matrix in this case. So in general it could be like Q by M, where Q is the number of cut sets and M is the number of edges in the graph. Okay, and here the entries are defined as follows. So here the rows are indexed by different cut sets and the columns are indexed by different edges. So let's consider the first cut set C1. Okay, so C1, it contains only one edge E8. Okay, so that says, okay, 1, 8, it will be set to 1. Okay, so equal to 1 if the ith cut set contains the jth edge. So C1 contains E8, so that says C18 will be equal to 1. Okay, that's how we set this entry. Okay, so let's look at one or two more examples. So in this case, let's consider C2. Okay, so C2, cut set C2, it contains, so this was our C1 and this is our C2. So C2 contains E1 and E2. Okay, so that says in our cut set matrix 2 1 will be equal to 1. Okay, you can say that 2 1 is 1 and 2 2 equal to 1. Okay, and let's consider one more. Okay, let's consider the cut set C5. So C5, it contains E3, okay, this edge, E7, okay, this edge, okay, and we are dealing with this cut set. Okay, so it contains E3, E7 and E6. Okay, so that says if you look at the fifth row, which corresponds to cut set 5, C5, so we are considering this row. Okay, that says C53. Okay, C53 will be equal to 1 because E3 contains E3 belongs to C5. Similarly, C57, 5, okay, 57 is also equal to 1 and 56 is also equal to 1. Okay, so that's how we define the cut set matrix. Okay, so similarly we will do the same thing for each and every cut set. Okay, C3, C4, C6, C7, C8, etc. So that's the definition of what a cut set matrix is. So let me repeat the definition. Let G be a graph with M edges and Q cut sets. The cut set matrix denoted by C, it is going to be a Q by M matrix, and again it is a 0 1 matrix with Cij equal to 1 if the ith cut set, okay, if the ith cut set contains the jth edge and equal to 0 otherwise. Okay, so here again we can see that if you look at this particular matrix, the some of the rows may be redundant. Okay, okay, so in order to get rid of those redundant rows, we deal with what is called a fundamental cut set matrix. So before that, okay, let's go discuss some simple observation related to the cut set matrix of a graph G. Okay, here again we can see that as we did with incident matrix and a cycle matrix, the permutation of rows or columns in a cut set matrix corresponds to simply renaming the cut sets and edges respectively. Okay, so we saw the same kind of situation with the other two matrices, insert matrix and the cycle matrix. And again we can see that each row in C of G is a cut set vertex. Okay, you can consider each row as a vector, a 0 1 vector. Similarly, if you consider the first row, so this can be considered as a vector. Similarly, if you consider the fourth row, okay, you can consider that as a vector, and so forth. Okay, and that's what this observation says. Each row in the cut set matrix is a cut set vector, and again a column with all zeros corresponds to an edge forming a self loop. Okay, because a loop, it doesn't form a cut set, and because of the reason, so anyway, okay, it doesn't have a loop or something like that. So we can see that if I add a loop here and I add one more edge E9 here, and if you look at this particular column corresponding to E9, okay, we will see that, okay, every entry will be equal to 0 because a loop, it doesn't corresponds to any cut set. Okay, so that's what that observation says. A column with all zeros corresponds to an edge forming a self loop, and again we can very easily see that parallel edges form identical columns in a cut set matrix. So this graph do have parallel edges E1 and E2. So that says if we look at these two columns E1 and E2, okay, they look identical. Okay, we can see from this example. Okay, so these are some simple observations about cut set matrices. Okay, so next let's talk about fundamental cut set matrix. So okay, this is nothing but it is a reduced form of cut set matrix. Okay, reducing some redundant rows from the cut set matrix, we get a fundamental cut set matrix. But the fundamental cut set matrix, it is defined with respect to a spanning tree. Okay, so let's see what a fundamental cut set matrix is. So let G be a connected graph with n vertices and m edges. The fundamental cut set matrix are denoted by C sub f. Okay, similar to the reduced incident matrix A sub f and the fundamental cycle matrix B sub f. Okay, so the fundamental cut set matrix C sub f of G, it is going to be an n minus 1 by m, where n is the number of vertices and m is the number of edges, and it is going to be a submatrix of the cycle matrix C, such that the rows corresponds to the set of fundamental cut sets, okay, with respect to some spanning trees. Okay, so this fundamental cut set matrix is defined with respect to a spanning tree and fundamental cycles. Okay, so let's consider this graph G. Okay, and let's consider this spanning tree, which is highlighted in red here. Okay, so that fundamental cut set contains edges E1, E5, E8, E6 and E7, and these three edges, okay, E2, E3 and E4, they are chord edges with respect to this red spanning tree. Okay, so let's consider that spanning tree and the fundamental cut sets with respect to some spanning tree. Okay, so in this case we can see that the different fundamental cut sets, okay, by definition fundamental cut set, it contains exactly one branch edge and one or more or zero or more chord edges. For example, in this case one fundamental cut set will be like E1, E2. Okay, so this is going to be one fundamental cut set E1, E2, so it contains exactly one branch edge and okay, one chord edge here. And similarly, if you consider this one, okay, so E1 corresponds to, okay, this fundamental cut set, and let's consider this fundamental cut set E5 and E3. Let's call that C2. Okay, so E5, E3, okay, that is another fundamental cut set. So it contains exactly one branch edge and okay, in this case one more chord edge, and okay, so these three edges form another cut set. So let's call that C4. Okay, so C4 contains E3, E7 and E4. Okay, so it contains exactly one branch edge E7 and two chord edges. Okay, and C1, C2. Okay, let's consider, okay, this, okay, these two edges E6 and E4. Okay, E4, E6. Okay, that is also a fundamental cut set. It contains exactly one branch edge and one chord edge here. Okay, and I think there is one more fundamental cut set, so let's call that C5. So it contains only this edge E8, okay, which is this branch edge. In that case it doesn't contain any chord edge. So that says, okay, with respect to this spanning tree, this graph G has 5 fundamental cut sets. So if you look at this particular matrix, okay, we can see that first row corresponds to C1. Okay, C1 contains E1, E2. Okay, E1, E2, and this corresponds to C2, E5, E3. Okay, and this corresponds to C3. Okay, this corresponds to C3. So C3 contains E4 and E6. Okay, and this corresponds to C4. C4 contains E3, E4, okay, and E7, and this is C5. It contains E8. Okay, so here what I did is I rearranged the columns in such a way that all the chord edges, okay, these three columns corresponds to the chord edges, and these 5 columns corresponds to the branch edge with respect to this highlighted spanning tree branch edges. Okay, so here the chord edges are E2, E3, E4. Okay, so these 3 columns corresponds to those chord edges, and okay, these 5 columns corresponds to the branch edges. Okay, E1, E5, E6, E7 and E8. Okay, so this is how we define a fundamental cut set matrix. Okay, and here we can see one important property of a fundamental cut set matrix. So we can see that the fundamental cut set matrix C sub f, it can be partitioned into two sub matrices, okay, one of which is an identity matrix of order n minus 1. Okay, so we can see that we can write this C sub f as two sub matrices C sub c and I sub n. Okay, for example, okay, if you consider this particular graph, okay, same graph here, and this cut set, fundamental cut set matrix. So here we can see that, okay, here this corresponds to this matrix, this sub matrix C sub c, which corresponds to the chord. That's why we have this subscript C, and here this corresponds to the branch edges. Okay, so here we can see that here we have this identity matrix of order n minus 1, okay, which corresponds to the branch edges. So if you look at the spanning tree, which is shown in this dark edges, okay, it contains 1, 2, 3, 4, 5 edges. So in this case, this is, okay, it is going to be a 5 by 5 matrix here. Okay, so here if you look at this particular matrix, we can see that, okay, we have this identity matrix here, okay, and this identity matrix corresponds to the branch edges of this spanning tree, and this C sub c, it corresponds to the chord edges, okay, this E2, E3 and E4. Okay, so that says a fundamental cut set matrix C sub f can be partitioned into two sub matrices, one of which is the identity matrix I sub n minus 1 of order n minus 1, where n minus 1 corresponds to the number of edges in the branch of the corresponding spanning tree. Okay, so that says we can write C sub f as, okay, the concatenation of these two matrices C sub c and the identity matrix I sub n minus 1. So where the last n minus 1 column forming the identity matrix corresponding to the n minus 1 branches of the spanning tree. Okay, so these edges, okay, 1, 2, 3, 4, 5, okay, n minus 1 branches of the spanning tree, and the first m minus n plus 1. Okay, so this thing, it corresponds to the columns forming the C sub c. Okay, this matrix corresponds to the chord with respect to that spanning tree. Okay, so in this video we saw the definition of what a cut set matrix is and what a fundamental cut set matrix is, and okay, we can always write a fundamental cut set matrix as two sub matrices C sub c and I sub n minus 1, where the C sub c corresponds to the chord edges with respect to a spanning tree, and this I sub n corresponds to the branch edges with respect to the same spanning tree. Okay, so in the next video we will show that the rank of the cut set matrix is also n minus 1, which is equal to the rank of the identity matrix.